Almost. Okay, let's try that again. Okay, so I want to look at page 46. I know you've done a couple of problems on page 46, and I want to talk about number 1, number 8, and then number 9. Just take a minute. 1, 8, and 9 on page 46.
Page 46.
Okay, so everybody take a quick look at, so number 1, I've got an MN graph, and remember, an NM graph. And remember what N and M stand for?
Yes, degree.
Very good. N is the order, number of vertices. M is the size, which is the number of edges. So forget graphs for a moment. Forget graphs. What can you tell me if I take, so this is problem number 1, if I take some real numbers, R1, R2, R3, let's say N real numbers. N real numbers. So this goes back to Math 3000. And so how would I take the average of those N real numbers? The average. I would add them up. Okay, so the average is, I use grown-up notation, the sum from I equals 1 to N of the R sub I divided by N. So that's the average of these real numbers. Now, degrees are just real numbers. So now, one of the first things you did in Math 3000 was show that the average of a set of n numbers lies somewhere between the smallest and the largest. So this is something that you know about real numbers. Forget degrees, forget graphs, just real numbers. If I take n real numbers and I take the average of the real numbers, then the average lies somewhere between the smallest and the largest. But in fact, degrees are just real numbers. So when if I take the sum of the degrees, if G is a graph with n vertices and degrees and d1 up to dn, then the average of the degrees lies between the average of the degrees, which, by the way, the average of the degrees is the sum of the di's over n. That's the average of the degrees. Okay, well, what's the smallest degree? What have we called that before? The smallest degree. Well, we had a name for it. We gave it a label, a Greek label.
Delta.
Which delta? Yeah. So delta is the minimum degree, and the largest degree, say delta, is the max degree. So if I take any graph and I look at the average of the degrees, then the average lies between delta and delta. Okay, is that clear? Okay, and that's what they're asking here in problem number 1. Let G be an NM graph. Show that the smallest degree. Oh, wait a second. he doesn't have this. Oh, that problem doesn't have that. Our problem has 2m. Okay, I've got an nm graph, n vertices, m edges, right? N vertices, m edges. So what am I going to put here? Okay, the sum of the numbers in the degree sequence. Oh, the sum of the degrees is what? What was that?
2 times.
Oh, so in fact, delta is less than or equal to 2m. Is that clear? Okay, that we're looking at the average degree. They're just integers. They're just real numbers. And in fact, it's nice because we know there's no negative integers. Okay, so we know that we have non-negative integers. We could have degree 0. We haven't talked much about graphs that have isolates. We haven't spoken much about it, but we could. It could have a vertex at degree 0. It's not very interesting. Okay, but they do exist. So questions about that? Okay, I'm just going to mention, just for us, so for a quick moment, I want to talk about number 2. Here, rather than an nm graph, I have an n2n graph. So what is the 2n, what does that 2n mean? That's what?
The size of
That's the
edges.
number of edges. That's the number of edges. Okay, and so what do I know? So how does, so I have an n2n graph. So the sum of the degrees, 2n is the number of edges, so the sum of the degrees, so I have some degrees. Let's just imagine d1, d2, dn. Okay, I have n vertices, and each of the vertices have a degree. Could be zeros, no negatives. Okay, so each vertex has a degree. So I have d1 through dn. What can you tell me? What this is an n to n graph. Is that right? So 2n is the number of edges. And what do I know about the sum of the degrees? Sum of the degrees is twice the number of edges. Oh, but what is the number of edges here? For twice 2n. Twice 2n, which is 4n. So I have the sum of n integers. The sum of n non-negative integers is equal to 4n. The sum of n non-negative integers, doesn't matter whether they're negative, is equal to 4n. Now, we know that that the minimum degree lies below it and the maximum degree lies above it. So if the maximum degree in this graph is 4, that would mean that I would be adding how many 4s to get 4n? N 4s. Oh, but we know that that either it's 4 regular, so that's 1, or what if it's not 4 regular? So if it's not 4 regular, they all can't be 4s, so one must be
Less than 4.
less than 4. And if one is less than 4, their sum has to be 4n. If one has to be less than 4, then what? One has to be greater than 4. Okay, so and remember, they're integers. They're integers. We're not talking about real numbers. So if one of the integers has to be greater than 4, then one of the integers is greater than or equal to 5. Okay. Now I'm saying a lot of words, and your job for this homework was to actually put that into words. Okay. Questions? Okay. All right. So I want to do number 8. And then I want to talk about cubes again, because I just love cubes. Okay, so take a minute, read number 8. New people, everybody, I got everybody's homework? Homeworks? Any more homeworks? Okay, we'll have digested number 8, at least what it's asking for. Okay, so let G be a graph, that's good, we're studying graphs, with min degree greater than or equal to k, where k is a positive integer. 1 is show that G contains a path of length exactly, notice it doesn't say exactly, but we assume path of length k. Now, what does it mean? What does it mean for when we talk about the path of length k? What does that mean? How do we measure path lengths?
So the number of edges.
Number of edges. Okay, so we want to show that there's a path, no repeated vertices, with at least k edges. Okay, so now here's something that you need to get used to. I'm not going to. We're going to assume part of the hypothesis. Well, not really. I'm going to choose a longest path. Now let's make it clear. This graph could have 1,000,000 vertices on it. It could have 12 million edges. I just picked 12 million. So it can have a lot of edges. And it may take you a long time to find the longest path. But you have all the time in the world, and you have computers, and you're able to find a longest path. Okay? So when I say choose the longest path, we know we can do that. We know that we can do that. Okay. So, choose the longest path. Okay, and I'm going to label it. I like x's, x0, x1, x2, and x. Okay. Now, the only thing else I know is that the min degree is greater than or equal to k. Now this is a longest, sorry, I'm abusing k. So this is the longest path. I don't know how long it is. I don't know how many vertices it has. I want to show that it has at least k vertices. At least k plus 1 vertices. A path of length k has k plus 1 vertices. Okay, so I want to show that this path, I want to show that m is at least k. Okay, notice I started at x0, x1, so if m is k, then that would be k plus 1 vertices. That's what I want to show. Okay? Yep. All right. So let's look at the vertex x0. Let's look at the vertex x0. So x0, if x0 had a neighbor, if x0 had a neighbor not contained on P. Okay, this is P. This is the path P. So the vertices on P are x0, x1, x2, up to xm. And if x0 had a neighbor not contained on P, let me draw a picture. So I have a neighbor of x0 not on P. What's wrong with that? What was it? What was that? Someone said it. Oh, this would be a longer path. This would be a longer path. But I chose a longest path. Is that clear? Is that clear?
Yeah.
One more time. I'm going to look at the vertex x0. I got a path from x0, and I've got x0, x1, x2 up to xm. If x0 had a neighbor not on P, then I would have a longer path. Does everybody see where the longer path is? Here to there. That would be a path of length, in this case it's length m plus 1. Okay, but we know the longest path is length m. So all of x's neighbors lie on the path. And how many neighbors are there? How many neighbors does x0 have? At least k. So let's see. The neighbors of x0 could be at worst x1, x2, x3. So m is at least k. So since the degree of x0 is greater than or equal to k, we know that it follows that m is greater than or equal to k. Is that clear? M is greater than or equal to k. Because if m was less than k, well, I got a problem. If m is less than k, then I wouldn't have enough vertices for x0 to be adjacent to it. X0, one more time, not adjacent to itself. We're not dealing with loops at this point. If m was less than k, x0 could be adjacent to x1, x2, x3, and it could be adjacent to xm. And if m was less than k, then the degree of x0 would be at most 1, 2, 3, 4, would be less than k. But we're assuming that the mean degree is greater than or equal to k. Okay, so everybody with me? M is greater than or equal to k. Yes? What's the length? What's the length of path? But then the length of P is how many edges are on this path? So how many edges? Edges. How many vertices? M plus 1. So how many edges? M. Okay, so we've now shown that there's a that there's a path of length at least M, or path of length at least M. Question? No? Questions about that? Okay, so that was part A. Show that there's a path of length. Everybody understands the difference between order and length. We showed that there was a path with at least k vertices on it. Okay, now we have to show that G contains a cycle where P is greater than a cycle CP. Okay, now remind me, what's the degree of x0? At least? Okay. Since the degree of x0 is greater than or equal to k, and all of x0's neighbors lie on P. Is that clear? Well, we already went through this. If x0 had a neighbor off of P, this wouldn't have been the longest path. Yeah. Okay, since all of x0's neighbors lie on P, a cycle, what are they? How does he want it? He wants a cycle CP where P is greater than or equal to k plus 1 must exist. Let's look at x0's neighbors. Okay, x0 could be adjacent to x1, x2, x3, x4, up to m, or xk, and that would give me a cycle of length k plus 1. A cycle of length k plus 1. So it will give me a cycle Cp where p is greater than or equal to k plus 1. Is that clear? So I know I said a lot of words, and you can't give me, you could give me a recording of your words. Now you have to learn how to write this into language that a reader can understand. Okay, that's your job over the next 2 months, to work on your proofwriting technique for this very different area of mathematics called graph theory. So about graphs. So we're going to really be spending a lot of time writing proofs, and dealing with these sorts of problems. Questions? So that takes care of. You should hopefully you've written down enough detail to be sure that you understand how you would prove all the words that you would write down, which are mostly here, number 8, 1, and 2, I and II. Okay, is that clear? Okay. One more time. Questions? Okay. So I love this graph. So we're going to spend a little more time with it. This graph. Hold on. I'll tell you what this graph is. I love this graph because it could relate many of the disciplines in mathematics that you've learned at this point to graph theory. Except it's discrete, and many of the classes you've taken in mathematics have been continuous in nature. But let's look at the 0, 1 vectors of dimension. Let's just say n, of dimension n. So is it clear what I mean by the 0, 1 vectors of dimension n? So my vectors are of the form A1, A2, dimension n. So A1, A2, AN. And they're 0, 1 vectors, so what can you tell me about each of the AIs? They're what? 0, 1. AI is an element of the set 0, 1. Okay? How many such vectors do we have? How many 0, 1 vectors of dimension n are there? How many 0, 1 vectors of dimension n are there? What was that?
Maybe 2 to the n.
2 to the n. Yeah. Let's see. I got 2 choices for this, and 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 2 choices for this. So I have 2 times 2 times 2 times 2 times 2. Yeah? Okay. So, and we've drawn this graph before. Let me label this vertex 1, 1, 1. And I'm going to suppress the parentheses and commas. So my entries, my entries are 0, 1. I'm suppressing the commas, and I'm going to label the vertices of a graph with all the 0, 1 triples, in this case triples, 0, 1 triples, but I'm going to change that in a minute to 0, 1 n-tuples. What's an n-tuple? You learned this in 3191, didn't you? Oh, that was a long time ago. It's longer for me.
Is it a vector with n entries?
Yeah, it's a vector with n entries. So I've got x1, x2, up to xn. Okay, so it's a vector of dimension n, and each of my entries are what? In this case, each of my entries are 0, 1. So how many are there? So how many 0, 1, forget triples, let's look at n dimension. How many 0, 1 n-dimensional vectors are there? Let's see. How many choices for x1? And x2? And x3? And xn? So 2 times 2 times 2 times 2 times 2, 2 to the n. So this has 2 to the n vectors. Let's just look at the triples where n is 3. So I'm just looking at the case when n is 3. So I'm going to label my vertices with x, y, z, where x and y and z are equal to are either 0 or 1. So once again, how many such triples do I have? How many such triples? Here I just, instead of x1 to xn, I just have x, y, z. So how many vectors do I have? 8, 2 cubed. 2 cubed? 2 to the third. Okay, so now I'm going to take these vectors and I'm going to make what's called the cube, or in higher dimensions, the hypercube. And I know we've talked about this before. So I'm going to label the vertices with the triples, x, y, z, all the different triples, x, y, z, where x, y, and z are either 0 or 1. Okay, that's going to be, now we're starting to actually look at graphs that take on a particular structure. Okay. And I'm going to put two edges. Now I'm going to tell you what, if I'm going to construct a graph, it'd be nice if I had some edges. So I'm going to put an edge between A1, A2, A3. And tell me again, A1, A2, A3 are what? Well, what A1, A2, A3 could be? A1 could be what? 0, 1. What, A2? And A3? Okay, so there's 8 possibilities. 8 possibilities. So I'm going to put A1, A2, A3 adjacent to, have we used this? This is adjacent to? Okay, adjacent to B1, B2, B3. If these vectors, and I'm using vectors, we're not going to use anything about linear algebra. We're not going to use too much about linear algebra at this point. Okay, other than the word vectors. If these vectors differ in exactly one component. Okay, so tell me, I have 1, 1, 1 up there. Tell me the 3 vertices, the 3 vectors that 1, 1, 1 should be adjacent to. One, 1, 0. One, 0, 1. And well, there's more points. How many points? How many vertices is this going to have if they're all? I'm going to use all of the triples. How many? 8. Okay, so far I have 4. All right, here comes some more. So I'm gonna label these 1, 0. Let's see. Let's put it 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, I have all the edges. Does 1, 1, 1 go to any of these? This is not a 0. That's a point. Sorry, I'm going to fill these in so you don't think those are zeros. Does 1, 1, 1 go to any of these? Remember, two vertices are adjacent if they differ in exactly one component.
No.
No, 1, 1, 1 differs from all of these in how many components?
2.
2 components. Okay. Well, what about 1, 1, 0? Does it differ from any of these in exactly one component? Which ones?
Middle one.
So this one and this one.
Yeah.
And what about 1, 0, 1? It differs from this one in one component. Notice it differs from this one in many components, and it differs from this one in one component. And what about this one? Okay, make sure I've done it right. Every pair of points that differ in exactly one component are adjacent. Okay, those are the only way you can have adjacency. But I only have 7 vertices. What's left? Okay. And is 0, 0, 0 adjacent to any of these up here? 0, 0, 0 differs from this one in how many components? This one and this one? Okay, what about this one, and this one? Okay, so now you see why, hopefully, you see why it's called the cube. Okay, in fact, we use Hypercube because now, I want you to take a minute, and now, what about 4 dimensions? This is 3 dimensions. Our vectors are 3-dimensional. What about 4 dimensions? So, 16 what? 16 vertices. How did you know it was 16? 2 to the 4th. Okay, so draw it. 16 vertices, and 2 are adjacent. 2 of the vectors, 2 of the points labeled by a vector, 0, 1 vector of dimension 4 are adjacent if they differ in exactly one component. Draw it. You're looking at me like, is he crazy?
I'm looking at that.
You're looking at this? Okay. Don't look at this. I've gotten used to it. Come on. Come on. You were looking at it. Come on. Come on. Well, what's the problem? It'll come eventually. Okay, you work. Don't forget this. I don't know what you did to it.
冻死了。
我终于把它打了。
Come on. Over here. I'm going to cheat. See what happens. Oh, this could be bad. Everybody got that graph? Not yet?
只要离不同，那就它们就是相同的，这是命名规则。
只要离一个不同的。
必须要离一个不同，如果是2个不同的不适合。
How many vertices does that graph have? Did we say that? 16 vertices.
Adjacent 就是这个不同，他们俩也超过一个不同，他们俩就不是相同的。